Thanks everybody for coming out today. Today we're going to be talking about digital transformation in aerospace. My name is Woodrow Bellamy. I'm the editor-in-chief of Rotor Wing International. And I want to take the chance to introduce our panelists. First we have Jason Rios, who is the Vice President of Aerospace at Sentient Science. Sentient Science uses material-based computational testing to simulate the reaction of complex mechanical systems in specific environments. So for example, they could take a helicopter engine, create a three-dimensional model of it, and predict its failures in specific operational conditions. Scott Drennan is the Director of Engineering Innovation at Bell. Just Bell now, as you all probably know.
Thank you for that.
To his left, we have Mark Moore, who is the Director of Aviation at Uber Elevate. And Mark actually has an extensive career in aerospace. He's formerly a NASA engineer. And here we have Dave Balevic, who is the Senior Vice President of Engineering at CHC Helicopter. They're one of the largest helicopter services providers in the world. They operate across oil and gas, search and rescue, and air medical. And we have Phil Herman, who is the Director of Marketing Services and Connectivity at Honeywell Aerospace. So again, just to let you guys know, we're talking about digital transformation in aerospace. If you're not using digital tools today, you're probably behind your competition. So we're going to go into a list of scripted questions. And then towards the end, we're going to open up for audience Q&A. So if you guys have any questions for these guys about the use of new digital tools in aerospace, you'll get the chance to ask them at the end. So first, I want to ask a general question to the entire panel. And we can start with you, Phil. So today, we're talking about, really, if you guys know what predictive analytics is, that's the basis of what we're talking about, predicting failures within critical systems on helicopter platforms. So Phil, as you know, the use of health usage monitoring technology has been around for a few years. What do you think the industry's been seeking within that type of technology, and what's available today that can change that process?
Okay. So, as he mentioned, Woodrow mentioned, technology's been with us for quite some time, and during that time, we're generating wealths of information, wealths of data. I think to the point that we may be overwhelming ourselves with that data and our just ability to ascertain what it all means. You'll see some conversation today about abilities to do analytics of that. And I think it starts there, the ability to sort through it and pick out the key facets that really apply to the problem you're trying to solve. How do you fly? How do you operate? How do you mission? But in addition to that, I think something we often miss is, do we produce a PhD answer, or do we produce a pragmatic one? Can I do something with the answer that comes out? Does it tell you to go fix or point you in the direction to do it, or is it just a beautiful graph and a nice thesis about what the problem is? So if I look at really where we're driving, it's better analytics, but it's a better way to put the answer in the hands of ultimately the person who has to maintain the aircraft or do something with it. That's just pragmatic. Thank you.
Dave?
Sure, let me give you the operator's perspective. We've got about 150 aircraft in our fleet. And today, health usage monitoring systems for us it's really a go, no-go. So it's a very primitive source of information for us. And I think that's the dilemma right now, is we're not asking the right questions. I've got a lot of questions. I don't have answers that are coming to me. Today, when we return back to a base from a flight, we download the HUMS data. That is done in a very manual process. We actually walk out to the aircraft. We remove a PCMCI card. We walk back to a hangar. We plug it in a computer. We boot up the computer. You get where I'm going. I think that technology really is something that could be advanced in terms of simplicity of getting the data and making the data available. Now, to your point, I think we also sometimes challenge ourselves with, are we asking the right question? And the most fundamental question is, am I okay to turn the aircraft around and fly another mission? We're not using the data right now to actually do as much trending as I think we should.
Scott?
Yeah, we have hum systems on several of our aircraft, and I agree with the two gentlemen here that one, you have to have smart big data algorithms so that you know you're getting data that you can act on, and also we struggle with our customers to give them more of a real-time feel for data rather than downloading. We do have some systems on board the V-22 that try to address that by giving the pilot direct actionable data. Maybe due to, relative to engine state, that we've been really successful in that area. Although what I'd like to see change about hums it's a very generic parameter that you always have to correlate to a specific area that you're really interested in. So I think a group like Sentient making that correlation tighter and more efficient, and then even providing perhaps a little bit of hardware at specific locations that we're more concerned with than maybe the generic vibration patterns that are coming out of the hub and everything.
And Mark?
So let me give you a little bit of the look into the future with what we're doing with Uber Elevate and why predictive health monitoring is going to be absolutely huge and critical. And that is, our buddies at Bell and Embraer and Aurora are developing electric vertical takeoff and landing aircraft. Vertical takeoff and landing aircraft, by their very nature, are complex. But what's really unique about this is that they're essentially all digital, right? Digital flight control systems, digital battery control, digital electric bus architecture, digital motor control to electric motors. It's all digital. Now that means that you have this wonderful ability to interface with lots and lots of data. And whichever part of the systems you're talking about, it's kind of a new world where we can do it purely from a digital perspective and be able to predict very much into the future where the issues are and be able to manage for us on-demand networks, not scheduled, but on-demand where everything's changing and these vehicles need to be incredibly interconnected all the time across these systems talking to our network operations center all the time in real time.
Jason?
Okay, so I think we kind of liken it almost to like a medical condition. If you're concerned about having a heart attack, you can hook yourself up to a heart monitor and kind of get the earliest indication of when something's about to happen and maybe pinpoint as the event's about to occur. But I think most people would rather engage with like a cardiologist who can look at your family history, can look at your lifestyle, can look at your individual risk factors, your body chemistry, and maybe give you some indications on what you can do to maybe offset something like a heart attack, maybe to change some of your behaviors in order to, extend your life. So we translate that to mechanical systems, and we look at there are opportunities to use what we know about the design or the materials to extend the life of those gearboxes and transmissions before we have to rely on the feedback from sensors that there's a crack occurring or that there's a bearing starting to spall. So we think there's opportunities to really extend the life of those systems in a meaningful way without having to continue to expand the amount of data that's being collected. We think there's enough data there to make those decisions. We kind of approach it from the first principles perspective and being able to look at the response of those materials and how they're going to eventually fail.
Hey, Woodrow,
Yes.
if you don't mind, Jason, let me just add on. I think the answers we've all given. We've got a diverse background up here. I think we would be mistaken if we only talk about failures and incipient failures. Let's not forget that there's a lot of opportunity out there to learn how to do things better. And that's one of the things that my perspective as an operator right now, we don't have feedback that's telling us this is actually a more preferred way to fly the aircraft, so that we can actually obtain what you're suggesting there. So let's not make it all avoid the downside. I'd rather exploit the upside.
Yeah, and that's a great point because really, there's a difference between maintenance and sustainment. With maintenance, you're fixing things that are broken or that are about to break. And we talk about sustainment, that's more of like a long-term commitment to the health of your fleet. And you would prefer to not do as much maintenance and to kind of leverage the sustainment practices to be able to get as much life out of those systems as you can. Sorry.
Second question, I want to focus on data sharing in the helicopter industry. I've covered the commercial airline industry quite extensively, and I will say it's a very data-driven industry. They all have minimum equipment lists. They have critical faults that they identify, and that kind of drives their business. Now, coming to Heli-Expo over the last couple of years, this is probably the first year I've actually had discussions about predictive analytics. So I want to start with Phil and go down the line. What type of data sharing exists today in the helicopter industry commercially between OEMs and operators?
It's going to depend, and we'll give it case to case. But data, we often get stuck in data about data ownership. We prefer to look at it data rights. You retain the data, and you can keep it locked away. But if you're not extracting the value from it, you're doing yourself no service either. We see the extremes. Data locked down, it's mine. I share with none. We see collaborative pools where data from multiple operators can go into a single place. I think if you can make it anonymous and take out some of that, it was this person who generated as opposed to it was these type of situations or platforms. So we're seeing that growing sharing. I think it's going to go through similar growing pains that the air transport. I came similarly from the air transport side. It's a possessive conversation. People will talk about owning the data. If you talk about data rights, you change the tone a little bit, and then you talk about how can we both extract value from doing it. We as a supplier will protect our data as well. I'll fully admit that. But we have to look at it collaboratively. And in this industry, it's starting to grow in that way.
Dave?
Sure. One aspect would be HUM's data, and I try very hard at CHC to open those pathways. We don't seem to be encumbered by a lot of concerns about data being shared externally. I think we have good relationships with our suppliers, actually really good relationships with other suppliers, and when they tell us that they're not going to share the data, we trust them. Those relationships are built on trust. But the data sources that we have, one of them would be HUM's, one of them would also be FDM, flight data monitoring, actually how is an aircraft being flown. But we also have some internal data. We have an ERP system that we use with respect to our entire supply chain. And then also we have another system that we actually use for scheduling aircraft in terms of the hundreds of pilots that we have flying around the globe. And I really believe that the culmination of bringing all those data sources together, there's some real power in that. So right now, I agree with what you're saying, Phil. I think there's a broad spectrum, some who are very apprehensive, but I'd like to think that we can together get past that through confidence in one another and trust in one another, and then start to use that data to really to affect the economic equation here for flying these aircraft.
Scott?
Yeah, so I'm going to go a little more negative. It needs to be a lot better, but I'm going to take responsibility for it as a service provider to folks like Dave. We have not done the right job explaining to our customers the benefit of what we can give back to them when we have their data and we put them through these analytical systems. The value proposition conversation's not there in either being ready for events where they need service, being ready to extend life because a given one operator is gentle on their vehicle, one is not so much. We need to do a better job as the OEM providing that value proposition, and then the trust corridor will open up and we'll put the best analytics we have on it to give the right answers.
That's fair enough.
So I'm going to keep my answer short because we're still working it out, but inherently when you look at Uber Elevate, Uber is stepping up to take on the network management side of things. Our manufacturing partners are developing the vehicles, and we're working out this middle area. But what we're convinced of is that there is this great opportunity for the manufacturers to step into some aspects of the operations. So from a data sharing perspective, we see the potential for them to be very, very involved in the maintenance and pilot training and how that data can all wrap together into a more optimized solution for the products that they're developing and then maintaining across these very, very large commercial aviation fleets in urban areas.
Jason?
So I think when you're talking about the value of data as you're trying to maybe manage the health of a fleet, there's a lot of value in being able to aggregate the data from multiple sources, multiple customers, and there's a challenge there because everybody's concerned about providing information into an aggregated environment because they feel like there may be some sensitive data that may be compromised at some point. So I think for us, assuring customers that there are techniques out there like differential privacy, for example, where you use complex algorithms to kind of mathematically sanitize the data so that it's physically impossible to reverse engineer the source. It gives people a level of confidence that they can share their data and start to benefit from the aggregated outlook without necessarily putting their own privacy at risk. So I think it's really important to have controls in place that assure customers of that in order to really kind of get maximum participation. Especially if you have a fleet that's used by the global community, well then you've got countries that don't necessarily want to share their data with other countries and things like that. So I think that's a really important part of it is how to assure them that that they can contribute to that without putting themselves at risk.
So I want to ask some specific questions to Phil, Dave, and Scott. Based on the tools you have, and I think you kind of touched on it, Scott, based on the tools you have today, how do you predict the forecast for demand of replacement parts? And I'll start with you, Phil.
Well, actually, they hit on it. I mean, the tools are great, and they give you an answer and allow you to project very traditionally, this part will break, I need this part to replace, consumables, et cetera. But by accessing the other database systems, we're moving into things like logistics chains, just in time. We're really being able, it kind of takes on other dimensions, really being able to expand a window, not just predict a part maybe 30 days out, but like 6 months out, and really start to be able to control your inventory. Go to shared inventory situations. So the suppliers that help with the operators is using these tools, understanding the trends and the analytics, we can better stock parts that they can share collectively, really bringing down their overall operating cost, reducing their risk. So that part of it, I think, is really advancing and really opening up and engaging those other systems that Dave mentioned about how they do ERP, how they fly, what are their operational plans, tying all that together, as opposed to just 5% spares. Just move away from that model.
Yeah, one of the things that we're working through within CHC right now is I'll try to give an example. If we break down aircraft maintenance into just two simple buckets, one being scheduled maintenance, one being unscheduled. We have an analytic model that we use to predict scheduled maintenance, and the accuracy of that model is actually pretty good. But it's also something that's pretty well understood. There's a maintenance manual that's published by the manufacturer. It's based on hours and flight hours and actually the calendar, and you simply have to follow that. So you should be pretty good at that. It's the unscheduled maintenance when something goes bump in the night, and that's the challenge. That's where we have to call up the folks at Honeywell and ask for an emergency, or because we've got an aircraft on the ground. Those are the challenges that I think face the industry right now, where we collectively spend a lot of money. One thing is the part's in demand, so there might be a premium for the part. Then there's going to be a premium for shipping. Then there's going to be an aircraft on ground, and the operator's going to pay a penalty. It's the value chain that makes complete sense, but boy, it gets really expensive. So I would suggest that my experience at CHC that this is an area that an organization like Sentient could really help us get our arms around and do a much better job. I don't think it has anything to do really with competition other than allow us to be smarter, more efficient, and therefore more economical.
Scott?
Yeah, we use a couple different methods. So I'll call known details, known assemblies that you put on your vehicle will determine mean time between failure, either from our vendors or from our own internal testing, apply a probabilistic analysis and try to get prepared for those best scheduled maintenance events that we can, and hopefully some of the unscheduled. We apply a mission spectrum that we develop between customers and the regulatory agencies, and we do our analysis to, through that mission spectrum to then predict these types of events. The other, best place is from the fleet. So we try to start early during flight test and count hours on what we call our fleet at that time, but then as we let the aircraft out amongst other users, that data can be invaluable as well. I think to Dave's point, You know, we feel that pain on unscheduled maintenance as well, because you're a customer and you have to wait, and we don't like that. And the only way we don't make you wait is we have a huge inventory stock, which then that eats into
Drives cost.
our profitability and your cost. So what we'd like to do with the unscheduled is to understand more about your operating parameters. So was there a particularly difficult environment that you operated in over the last couple missions? Sand, say, for example, or other conditions that might help our engineers look more specifically into failure modes that we've considered but didn't consider, repeatable to a significant extent in most missions.
Maybe a follow-up question, Scott. Are there specific parts that you focus on that are more likely to fail than others?
Well, so I'll actually segue this into a great talk for Mark as well. Everybody knows that the hubs on a helicopter are complex mechanisms. There's rotational systems both there and in our transmission, so those are the places we're most concerned. There are some airframe items that have complexity. It's mostly based there in the airframe because it's redundant. It's harder to predict where things are going to actually happen, but the redundancy also helps you not worry about it as much. But some of the opportunities in distributed electric propulsion, they simplify the hub. Our goal at least is to eliminate transmissions completely. That is mechanical transmissions. There's an electrical transmission system in those. So those are opportunities there as well to do better on unscheduled maintenance in particular.
Okay. So Jason, Sentient Science is a first-time exhibitor this year at Heli-Expo. If you go to your website, it will tell you about 3D materialistic science.
Yeah.
Can you kind of break that down a little bit and explain what that means for the helicopter industry, what you guys have already provided for the military, and what you can provide for the civilian?
Yeah, so I think just kind of for the user community, what it kind of means is when we look at a gearbox failure, we look at three basic elements, the when, the why, and the how. Right, so the when is pretty self-evident, right? That's the timing of the event. There's been a lot of effort and resources put into, figuring out that timing over the past 10, 15 years with hums and things like that. There's been a lot of good work. It's very important. But we think that when you look at the why and the how, to us, those are material science questions, right? So the why, it goes kind of to root cause. You start looking at what is it about the operating conditions or the design considerations or just even the material characteristics of the base material of those components that's contributing to the accumulation of stresses that are eventually going to cause cracks and failures. Excuse me. And then you look at the how. And for us, that kind of goes to the failure mode. When the system does fail, how is it expected to fail? Are you expecting to see hitting in the gears that are going to develop cracks, or are you looking at maybe spalling in the bearings that are going to cause those bearings to become the life-critical part of that gearbox? So kind of being able to understand all three elements of that failure is really what enables operators and OEMs really to get more visibility on these failures, to be able to kind of look farther out and to be able to perhaps reduce some of that safety stock that's causing so much headache as far as affecting operating costs and things like that. And so we've seen we've had a lot of opportunity to explore this in the wind industry, where our technology has been very widely accepted, and what our customers have found is they can see a line of sight to perhaps 10 to 15% overall reduction in their operating costs based on being able to tackle things like inventory, being able to schedule their maintenance more efficiently, right. Being able to hit some of those things that really you would prefer not to spend your money on. And so that's where we think the value of material science and in aerospace industry really lies, is just to kind of be able to kind of look a little bit farther out, based on science, not necessarily based on a statistical analysis.
So, go ahead.
Yeah, I applaud that answer, because that's where we need to get to. We're not there today. I believe my experience would tell me we have an industry that's ripe to get there. We've got numerous examples that are demonstrated. And again, we have to stop talking about just diagnostics, but more about prognostics and how to get out there in the future. And if you simply think about just, it's a very complicated system, an aircraft. And again, back to another example, let's just talk about fixed wing, takeoff and landing. What's the throttle position to maximize efficiency? The point of fuel burn is going to turn into millions of dollars, and that example has been demonstrated. I don't think we can sit here and put our hands on 5 examples today within the rotorcraft industry, and we need to get there.
Right. That's great.
I'll jump to Mark. So Uber, I think everybody's aware of your ambitions to do electric-powered air taxis. Can you talk about how you use digital tools to make that economical, right? So today, if you get an Uber car, it's economical for an operator. But if you think about an air taxi, very expensive to operate a helicopter. How do you use digital tools to make that future operation economical for the operator and the passenger?
Yeah, there's really 2 keys towards favorable economics for this new Elevate air taxi system, and that is getting the load factors filling up the vehicles with passengers. We do that on the ground with a product called Pool, where we actually are able to aggregate people still with on-demand trips to have the vehicles pick up different passengers and fill that vehicle. We're going to be doing the same thing in the air. We're going to make sure that as we fly from skyport to skyport, that we're going to be able to pull on-demand customers together to fill up the vehicles. So load factor is critical and requires a lot of data. It's a data-driven problem to match all those trips together. The other side is utilization of the vehicles, right? You got very expensive vehicles that need to achieve high utilization. Currently, with the helicopter industry, utilizations are more like 300 to 500 hours per year. We are talking about being able to do what the Bristols do with oil services, 2,000 hours per year. That is utilization is the key to driving to a high affordable transportation products. Now, if you're driving to high utilization, 2,000 hours per year, guess what? You've got to make sure those vehicles are always well maintained, and we know when they have to go into service. And so again, it's a very data-driven problem to get to high utilization on these relatively complex vehicles, especially as you're looking at systems like the battery, right? I mean, that battery needs to be able to land, charge in 5 minutes, and take off the next customer. That battery is a really expensive part of the vehicle, and you've got to know not just the voltage and temperature, you've got to know how much each one of those 10,000 cells is stressed. And that's a data-driven problem where you need to be able to predict how quickly you can charge the different modules and make sure that you can extend the life, so that you don't just get 500 cycles of life from these batteries, but can move that up to 1,000 to 2,000 cycles. Everything we're talking about to get to these high utilization and high load factors, it's all data-driven.
So I'll just ask one more question and then open it up to the audience. Scott, you lead a very exciting division at Bell, Innovation. I think you guys stood it up recently. Can you talk about new innovative approaches you're taking to predict failures in your existing fleet?
Yeah, so at Bell, I think everyone's heard about the digital thread. At Bell, we like to talk about the digital fabric, because what we're finding is that if you don't start this digital fabric from the creation of the part itself all the way out to the maintenance actions that we take for our customers or help our customers with, then you've missed all the power and leverage that you can get from the correct use of the data that we have out there. So it extends not only, so that you just walk through it a little bit, digitize design, create the part, digital twin then that resides with that part as it travels through its life. The data that we get from the operations of the aircraft then is reflected back on that digital twin. We put predictives on it, like product from Sentient Science, and you know what's happening to that part, and you're watching it in a digital space as it goes through its physical life, and then you know all the spots where you have to jump in early or stock up your inventory or be ready for a real-time decision to be made to help the pilot with fuel or other operational parameters. That's how we think the future needs to go, and those are the kinds of things we're looking at Bell.
Let me see if we can build upon that.
Sure.
Because we're still talking about failures again, and I want to get past that.
Yeah.
Would you suggest that also that rich environment of data is going to make the product team smarter, so they can actually figure out how to get more out of the existing design?
So I always call it my holy grail, and it involves my past life as a structural analyst. When I look at missions that we certify the aircraft to, I know that it's a mission that not everyone executes. So if we can find folks that do a, let's call it softer or more benign mission, we should be able to extend the life of that aircraft and extend the usage spectrum of that aircraft. So I think that's one of the positive pieces of it as well. But I do think it is better to look at it from the potential side. It's about the operator, the pilot who's a mission and safety officer, being able to make right choices, not only about safety, which we're all concerned about, but the mission going exactly as planned. And there's all kinds of data that you don't have to wait for until you land, that you could actually give the pilot to help them do that.
Yeah, I was hoping that would be the answer, because I look at it today similarly, that there's a spectrum that you design to, and it's somewhere between 1 and 10, and not everybody flies at a 10, but we all have to perform maintenance based on a 10.
Yeah, we have we've worked with the FAA on this. We have a project called Mission Link, and besides keeping inventories under control, it's also about trying to find a path where we might be able to enable basically tail number specific lives or tail number specific spectrums.
Do you think we'll get to condition-based maintenance?
I think we can. Yeah, and it's all about just collaborating with the FAA in the right way and making sure they know what data is available to us and what analytical tools we apply to it to make that answer correct for them.
And there's models today to that end, like engines that do on demand and on condition maintenance, and you want an engine to work, right? Especially when you're over the water. So I think you're on the right track. Absolutely, the precedence is there, exploiting the data. I love how you do it, because you put in that positive sense. If you're going to make the investment to put the equipment in, and shockingly, it's neither free nor zero weight and zero cost. But those positive contributions that data generation, collection, transmission can make, not just on availability, it's hugely important in your asset utilization. I can complete the mission better. The same equipment that's supporting a positive outcome, not a failure, a positive outcome, can also save a life. The very same equipment that's transmitting the maintenance data off the aircraft can transmit telemedicine information. I don't have to wait till I land, I save that patient. The FAA actually has a price on the value of life, if you're interested in the model. So absolutely, that positive outcome all the way through, how you operate your aircraft. We do this on the air transport side. We pull data, make it ambiguous who contributes, but we can model your particular performance of your airline relative to that platform set and show where maybe you should deploy your gear later or your flaps sooner or those kind of trade-offs, delivering 3-4% fuel efficiency.
Huge.
OEMs will redesign an airplane
For tens of
for 3 to 4, spend tens of millions of dollars to do it. So it's those positive outcomes. And at the end of the day, your aircraft was still more available too.
Right.
And you save inventory, logistics, the airfreight. So yes, big dream.
So we have an audience question.
Sorry?
Go ahead.
Oh, no you don't.
One question. Do you guys see any glaring technology gaps to be able to do this kind of thing better? We talked about analytics, but are there other technology gaps that would make it easier to do this?
Let me weigh in before the experts do.
Oh,
I would suggest that there's a lot of low-hanging fruit before we get to the need for additional technologies.
Yeah, I think I agree with that. I mean, the simplest is the most elegant usually, but we could use some lightweight hardware to help us really get into some of the problem areas in a finer way. When we flight test vehicles, we have them instrumented to within, an inch of them, getting uncovered by strain gauges and whatnot. And then when we get into operational model, we have to let go of that because it's not realistic or practical for the vehicle. So I think some hardware improvements in sensing, perhaps a wireless system or optical systems that don't burden the vehicle and the vehicle systems that are critical for operations could help a lot in this area. And then we could focus on some of those particular spots.
And I'd like to add something to that. I think, because we kind of focus on drive systems, we look at gears and bearings a lot, and there's a lot of new materials out there. There's a lot of investment going into developing high performance materials, lighter weight, stronger, more heat resistant. And so the technology is there, I think, but when you talk about the cost of incorporating something like that into a platform is enormous, right? So Scott, you probably know better than I do. Yeah. What the obstacle is there, but I think what we're trying to work within the industry to do is maybe lower that cost by being able to address the way new materials are qualified for geared systems to maintain all of that due diligence and that safety factor and everything, but make it more affordable so that those technology advancements can actually make their way into platforms quicker. And maybe we can develop lighter weight, stronger drive systems without it being a $100 million investment for Bell. Because, if it is, then if it's that expensive and it takes 15 years, people aren't going to do it on the current generation of aircraft. They're going to hold on to that till the next thing comes out.
Yeah, Jason, Mark. Jason and I work together on projects like this, and their analytical tools are amazing. And the analysis part is always the answer, but I think one of the details I'd like to talk about that you addressed is those when you put a piece of hardware in there, it doesn't mean the analytics go away. In fact, the analytics get validated by the hardware, the data, the empirical data, and vice versa, and then suddenly you can start to release that burden off the aircraft. So it's not about eliminating the analytics. The analytics are where we want to go with it so that state conditions all along the road, but they can enable each other, but it's hard to pay for the overhead with some of the current sensor systems.
Yeah, I'd like to add a key difference between the type of vehicles that our partners are developing and what exists today is the level of distribution that exists, right? We're talking about aircraft that instead of having one gearbox and one or two engines, they have 6 to 12 motors. They're not engines anymore, they're motors. We have energy storage systems that instead of being one fuel tank is 10,000 cells. So this level of distribution that is inherent in these electric VTOL aircraft suggests that instead of having centralized data collectors and sensors, that we're going to need to go to highly distributed sensors and data collection systems. That means much smaller, much more lightweight, much lower cost, maybe even less capable because we'll have redundancy inherently built into this highly distributed system, so we can actually select that they're lower reliability because we have much less sensitivity to a single failure.
Okay, well, that was an exciting discussion. I want to thank Sentient Science for hosting and sponsoring this panel. And thanks Jason, Mark, Scott, Dave, and Phil for joining us here. I'm sure if you all have any other questions, they can answer them after the panel. So thank you all for attending.
Hey, thanks.